let's talk about the next phase in your probability education, okay? So the topic of today's lecture is kind of a follow-on from this idea of the probability mass function, and it's called the cumulative density function, which is a simple idea, and it's going to lead us into the more complicated world of continuous random variables, okay? So today's topic is what's called cumulative density functions, or CDFs, okay? And you're going to see this CDF abbreviation a lot going forward, okay? So let's go back and remember what did we mean by a probability mass function, a PMF. So remember the definition of a probability mass function, right? PMF. So basically, we do some experiment in our sample space. We take an outcome from that experiment, and we turn it into a number on the real line, right? So these are the possible values of that experiment, right? Dot, dot, dot. Could be the number of heads in a bunch of coin flips, could be the time until we get a first head, that kind of thing, right? And so we wrote the probability mass function in the following way, right? The probability that the random variable x is equal to k is, basically, we drew it like a bunch of arrows like this, where these were the possible values of the random variable, right? And we know that if I add up over all the possible values, the probability mass function, that these have to sum to 1, right? There's kind of a single mass of probability that totals up to 1 when I add up all these arrows, right? And so life is easy when I've got a finite number of arrows and I can just add them up. Life is a little bit trickier with something like the geometric random variable where I've got an infinite number of arrows. But as long as the arrows are getting small enough that when I add them all together I get 1, then life is good, right? And so what is this cumulative density function, this CDF, okay? So it's related to the PMF. So the CDF, and I'll write this down again just for completeness, cumulative density function, of a random variable is basically, so here's the notation. Big F, big X, and then say little x, okay? So this is big F, big X, and the big X stands for the random variable, and then the little x is basically some number, some real number. And that's defined as the probability that this random variable, big X, is less than or equal to little x for any value of x. Right? So what's the probability that the random variable is less than a certain value? A simple idea, right? In some sense, you guys already were solving problems like this on, on the exam, right? So we asked, for example, on one of the exam problems, what's the probability that x is less than 3, that kind of thing, right? And all I would do is I would add up, in our previous world, I would just add up the corresponding sticks, right? So kind of like, let's kind of take a look at an example, a concrete example. So for example, I could, look at a binomial with n equals 3 and p equals a half, right? That's like flipping a coin 3 times and counting the number of heads with an equal probability of each, right? So here my sample space is 0, 1, 2, 3, and my PMF looks like, not too hard to compute, that the probability of getting 0 or getting 3 is 1/8, and the probability of getting 1 or 2 is 3/8, okay? So everything is nice, the arrows add up to 1, and now I can think about what is the CDF for this random variable, right? So that's like asking myself, okay, if I'm going to draw a line somewhere, what's the probability to the left of that line, okay? So clearly, if the line I draw is to the left of 0, then the CDF is 0, right? Because, you know, if I have some number like -1, that's like saying what's the probability that I get less than -1 heads, right? It doesn't make any sense. So I can see that certainly if I'm less than 0, I have no probability. If I am, on the other hand, kind of way over here, right, if I'm like out here, then I have all the probability, right? So if x is greater than or equal to 3, then I have everything, right? And you know, then I can ask about the probability of any number. So the interesting stuff, of course, is happening between 0 and 3, right? So if I were to ask for what's the probability that I'm less than 1.5, for example, right? So like the probability of the CDF of 1.5, what I would get would be I would add up the impulse at 0 and the impulse at 1, and that would equal 1/2, right? And I would get the same answer if I asked about the CDF at 1.6 or 1.8, right? So basically, in this case, there are going to be kind of plateaus where the CDF is constant. And so let's draw out then what does the CDF look like. So what we get is kind of like a stair-steppy looking function. So up to the point 0, this is my CDF. Up to the point 0, I have nothing. You come from nothing, right? Now, at the moment that I hit the 0 impulse, right? So just, I mean, any number that is even slightly infinitesimally less than 0, I'm still at 0, right? The moment I hit that impulse, I accrue 1/8 probability, right? So as soon as I hop over that impulse, I hop up a step to the value 1/8. And then I'm at 1/8 for a while. Right? So again, just a quick reminder what this notation means. This is maybe ancient calculus notation. What it means is that, you know, when I draw a step function like this, I have to kind of be careful about, you know, what is the value at exactly 0? Is it 0 or is it 1/8? And this closed dot kind of tells me that, you know, that's where the value is, right? So up to, just right up to the edge of 0, I'm at 0, and then I hop up to 1/8, right? Then, as soon as I bump over the impulse at 1, I accrue another 3/8 of probability. And then when I bump over the impulse at 2, I accrue another 3/8 to get up to 7/8. And at the end, after I bump over the impulse at 3, I end up at 1, right? So if I've had any sort of sense of scale, everything after 3 is landing at 1, right? So basically, hopefully, this kind of follows from our definition, right? And so now, if you ask me, hey, what's the probability of f being less than 2.5? I look it up on my graph. I say, oh, 2.5. I follow this up. It's 7/8, right? And so now, the reason that I like to draw my PMFs as delta functions hopefully is becoming a little bit clearer, right? Because actually what I'm doing is I'm integrating, right? I'm integrating the PMF to get to the cumulative thing, right? This is exactly, you know, the definition of cumulative, right? I'm saying, tell me about all the probability from -infinity all the way up to the point that I care about, just to the edge of that point. This negative means just to the edge of that point. Integrate the PMF dy. Okay? And this is one of the reasons that we ask you to be taking signals at the same time as probability, right? Because you have hopefully by now learned all about delta functions and step functions, right? We know that the integral of a delta function is a step function, right? We all know that. Just let me refresh our memories in case some of us are not quite there yet. So remember that the definition, in some sense, of a delta function is that when I integrate a delta function, I get what's called a step function, right? So this is what we call a delta function. And this is what we call the step function, usually denoted as u, right? This horrifying possibility that the worlds of signals and probability are colliding, right? You never thought that you'd have to do it in both classes, right? Luckily, this is not like a big, theme of the rest of the class, but today we're going to talk about it, okay? So just kind of like thinking about this is like saying, okay, if I have a delta function that is, sitting at 0, right? And I want to know, what do I get if I integrate over that delta function? It's like saying, well, if I draw my line anywhere to the left of 0, I get nothing, right? 0, 0, 0, 0, 0. And then as soon as I hit the impulse, I accrue 1 unit. And then from there on, if I were to draw my dividing line like over here, I've got just 1 unit of mass, right? And this is exactly what we think about as the step function from signals and systems, right? So this is the delta, and this is the step. Okay, let me pause and ask. Any questions about this? So if I want to be really, literal-minded and look at my, PMF. So let me kind of talk about this more generally, right? So I kind of already did an example where I took a PMF and I derived what the CDF was. Let me do that more generally. Yeah, question? Oh, what's the meaning of this dash? So this basically means kind of approaching x from the left. Right? Kind of means I am just up to that point, right? And so let me kind of go back and talk about, okay, now I can think about writing a PMF as just a sum of a bunch of delta functions, right? So, for a general PMF, right? I can think about saying, okay, my probability mass function is like the sum of a bunch of scaled and shifted delta functions, right? So it's like saying I have a bunch of probabilities at each location, right? And so here's kind of a picture. I have, x1, and here's the probability of getting x1. And I have x2, and here's the probability of getting x2, and so on, right? And so that's now I could put this formula and I could apply it to binomial, geometric, whatever, right? If I were to then say, what is the CDF is saying, okay, I am going to integrate this PMF up to the point x, and I'm leaving off the little minus sign for the purposes of making this a little bit easier to understand, right? And so this is like saying, okay, what do I get if I were to integrate what I know this PMF to be? This PMF is actually the sum of a bunch of delta functions. And to be honest, I know that this, I think this notation kind of even obscures a little bit what's going on. The insight is basically pretty simple. It just says that, every time I bounce over one of these delta functions, I add up that amount of probability, just like we did in the binomial example, right? So that's like saying that the corresponding CDF is just going to be the sum of a bunch of delta functions that are kind of getting added up and that are turning on at the various possible outcomes, right? So for example, in this case, it's like saying, you only draw one more arrow here to make it interesting. So in this case, it's like saying that if this is my PMF, that my CDF is going to look like, a delta function, or I'm sorry, a step function that turns on at x1 and is as tall as px of x1. And then it's going to have another piece that turns on at x2 and is as tall as this. And then it's going to have another piece that turns on at x3 and is as tall as that, right? And so on. And so the result that I expect for any sort of a discrete random variable is that my CDF is going to look like kind of a stair-steppy function. Right? It's going to basically look like, it's going to be 0 for a while, then it's going to turn on, and it's going to have a bunch of stair steps, and eventually it has to end at 1, right? It's going to basically be a sum of step functions. So questions or comments about this? Let's just do this for a couple of other familiar random variables, right? So let's suppose that I have a uniform random variable. Right, so suppose I roll the die, like I have an n-sided die with the possibilities 1 through n. A fair n-sided die, so everything is nice and fair. That means that my PMF, I know, looks like a bunch of equally sized impulses. This is my PMF. And my CDF is going to be just a nice, even, happy stair step that starts at 1 and then tops out at here, and the value of this is 1 over n, and the value of this is 2 over n, 3 over n, ... Easy. Okay? Now, what if we have something where we have lots and lots of outcomes, right? The infinite outcome case, like the geometric random variable, okay? So the geometric random variable, your old friend, so let's remember what our definition of that was. The PMF was something like this: k minus 1 failures and a success, and the possible values of k went from 1 to up to infinity, right? And so again, let's think about what the CDF should look like. So let me kind of draw some pictures on the right-hand side and some numbers on the left-hand side, right? So this is like saying, okay, certainly I have to have at least 1, right? And so, the CDF for any number that is less than 1 has to be 0, right? I have to have at least 1 coin flip, right? And then, at the moment that I pass over 1, I increment my CDF by the probability of getting 1, right? So the probability of, if I'm in the range between 1 and 2, how much probability have I got? Well, it's like I succeeded on the first try, so I have P probability, right? Now, if I ask how am I doing between 2 and 3, my CDF is like saying, okay, I take the probability of getting it on the first try plus the probability of getting it on the second try. So that means I am jumping up a little bit. Important to note, right? The CDF is always increasing, right? It can never dip down again, and so on. So in general, if I want to write the formula, I'd say that if I am, and this is going to be like a mess, so let me think about this for a second. So basically, it's like saying it's the sum from k equals 0 to n minus 1 of 1 minus p to the k times p if I'm in the range between n and n plus 1. Again, don't freak out about this too much, but this is just kind of like being very precise. And remember what's happening is that, remember that P is a number less than 1, right? So 1 minus P is also less than 1. So every time I add something new, I'm adding a little bit less than I added before, right? Because here I'm adding P times something that's smaller than 1, right? So every stair step is a little bit shorter than the last. And that clearly has to happen because my stair steps have to approach 1 in the limit, right? So I know that in the end, at infinity, I have to approach 1 as kind of like an asymptote, right? No single number will get me there, but as I go on, these stair steps get finer and finer, right? So basically the steps get, I'm going to just label my axes because I'm always on you about labeling your axes. So basically the steps get smaller as we approach 1. Well, as we approach infinity, let's just say. And the limit is 1, right? Okay. And because I feel like we've all had enough of the infinite sum formula, I'm not going to simplify what this is. You could do it and get a formula for it, but let's not do that right now, because I know you're all still hurting. So, all right, so any questions or comments about this? Okay, so this leads me into this new world, right? So everything we talked about so far is purely discrete random variables, except for the kind of pictures of the square and events and stuff like that, right? And that was actually, I guess, okay, I take it back. We did talk a little bit about this concept of events that have continuous outcomes, like number 5 on the exam, that are just going to be some real number, right? And so now we're going to generalize that concept to the general idea where I do an experiment and I could get any real number, not just one of a discrete set of possibilities, okay? Those are called continuous random variables. So now we're ready to talk about them. We have all the machinery. So now we're ready to talk about continuous random variables. And almost everything we talk about for the rest of class will be, or not just this class, but the rest of the course is going to be in the continuous world, okay? So we kind of lull you into a false sense of security with coin flips and die rolls, and then we introduce like the heavy duty stuff, right? So the setup is basically same kind of idea. We have some sort of a experiment. And this kind of is like the sketch of the sample space of the experiment. I get some outcome. I have a random variable that maps that outcome into just some value, right? Could be anywhere. Doesn't have to sit at a given discrete set of locations, right? So x can be, that's a new sound, any real number. Not just one of a discrete set of possibilities. Okay? So let's do an example of that, right? Okay. So for example, let's suppose that we look at how long this class lasts, right? So let's say that x is the length of time the class lasts. Okay. And let's suppose that we call this a uniform random variable, and so now this uniform random variable is going to be continuous, not discrete. Okay. So this is a uniform random variable. Say between 70 and 90 minutes. I mean, realistically, in this class, I probably don't even go to 70 minutes, but all right. That's what I have in my paper, so that's what I'm going to say, okay? Okay, so let's think about what does the corresponding CDF have to look like for this. And so in some sense, I'm introducing to you, I'm defining for you, what does it mean for the random variable to be uniform, right? So I'm going to draw it for you first. So the probability that class lasts for less than 70 minutes is 0, right? The probability that the class lasts for more than 90 minutes, I'm sorry, less than 90 minutes is 1, right? Because after 90, I've accumulated all the probability that there is, right? And so what does it look like in the middle, right? So kind of intuitively, you know, if I ask about the probability that the class lasts 80 minutes, that number should be right in the middle, right? So I mean, it should be equally probable that I'm less than 80 or greater than 80, right? And kind of similarly, you know, what's the probability that it lasts 75 minutes? Kind of the intuition is that that's like a quarter of the time gone by, and so that should be like here. And so the definition is that I basically just draw a straight line that connects these 2 points. So let me just write down what I just said. So the CDF is clearly 0 if I'm less than the lower limit, and it's clearly 1 if I'm greater than the upper limit. And it is, for example, you know, if I look at what's the probability that it lasts that lasts less than 80 minutes. Let me just remind you, this is the probability of being less than 80, right? If I look at this picture, it's a half, right? That's kind of like the intuition saying that, you know, this is kind of halfway between the 2 values, right? And now let me kind of, the reason I caught myself, right, is remember, this is like the probability of an interval, right? So let me remind you, it's kind of like the probability that the random variable is anywhere in here. And the counterintuitive part, the first time you see it, may be, you know, what is the probability that x is equal to 80 minutes? Exactly. What do we think? 0. That's right. The probability that x is exactly this number is 0. How could that be? That seems kind of weird, right? But let's think about it this way, right? So again, so maybe if I phrase it a slightly different way, you know, let's look at some intervals that are containing 80, right? So if this is my intervals from 70 to 90, and here let me draw 80 in the middle, right? So I could ask, okay, what's the probability that I'm in like this interval here? Well, kind of if this is a uniform distribution, kind of I've got some sense that the probability should be a half, right? Like between 75 and 85, right? What's the probability that I'm between here and here? Well, that's a smaller number, right? Maybe equal to a quarter. What's the probability here and here? Well, maybe that's equal to an eighth, right? And so then if I ask, like, you know, what's the probability that I am within 1 nanosecond of 80, right? That seems suddenly very unlikely, right? So the probability that I'm exactly 80 in the limit is 0, right? Kind of the way to think about this is that if the probability of any number inside this interval was not 0, then I would suddenly be way above 1 when I started to add them all up or integrate, right? So that's kind of the important thing for continuous random variables, is that the CDF is always talking about the probability over an interval, right? And that's where the probability is. Any single dot on the interval doesn't have any probability associated with it at all. It's probabilistically extremely unlikely that you get any given value. Question? Right. Okay, but so good question. Let me repeat that. So basically, you know, how does the PMF come into this, right? The answer is that we haven't talked about that yet, because in some sense, I got to the CDF by integrating. So I should be able to get back to something by taking the derivative of this, right? And that derivative is what we were going to call the PDF, the probability density function, right? That's next lecture, right? So basically, the PDF is like the generalization of the PMF, right? And the derivative, just like we integrated those delta functions to get to that stair-steppy thing, we can take the derivative of the CDF to get back to this probability density function. And that PDF is really like this super central concept to probability. So put a pin in that until next time, right? I'm not going to talk about PDFs today, but that's where we're going for sure next week. Okay. So let me just kind of restate kind of what I was saying is that, you know, the probability that I am in, you know, like I'm within 80 plus or minus 1 nanosecond is super small, right? So that's why kind of the probability that I am exactly equal to anything in the limit has to be equal to 0, right? But what I'm going to use the CDF for, and what the next homework is about, is basically, you know, now that I've got this kind of a description of how the random variable behaves, I can get the probabilities for any interval that I want, right? So what I could say is, okay, you know, so we use the CDF, or we can use the CDF. We can use the CDF to compute the probabilities that x is in a given interval, right? Because the probability that my x is, say, between x1 and x2, right? That's like saying the probability that x is less than x2 minus the probability that x is less or equal to x1. And these can both be phrased in terms of the CDF. So in some sense, the CDF lets us kind of read off the probability of any given interval just by looking at the CDF values at those endpoints and subtracting them, okay? I'll do an example of that in just a second. And let me just say, in case you're somehow disturbed by the fact that I'm kind of being a little bit slangy about saying less than versus less than or equal to, the reason I don't really care that much in the continuous world is, as we just talked about, any given value has probability 0, right? So really, I don't have to worry that much about whether I put a less than sign here or a less than or equal to sign here, because the probability of being exactly at a certain point is 0. Question? I start big S and small. There aren't that many S's here. Oh, big X and small x. Can I stop doing that? It is confusing, right? But that's the way it is, right? So I need to be a little more clear. Hopefully, you know, I hate to give you that answer, right? That's the way you're going to see it in all the probability books and references you're ever going to see. And I know it is confusing that there's a big X and a small x, right? So the thing to remember, right, is that the thing that you see here is always kind of like the name of the random variable, right? Which is usually a big letter, right? The thing that you're going to see here is basically a particular value. And you're right that there's no reason why I couldn't, for example, talk about fx of z, right? Which is basically the probability that big X is less than this value, right? Or y or whatever, right? But it would get a little bit confusing, I think, as you would see in the long run, right? So eventually, you know, if I have two random variables, x and y, and I want to talk about some probability being a certain place, then I got to have two other variables for the possible locations. It would get even worse, right? Because you have to remember which thing goes with which. I think the reason that they do this is that, you know, here you kind of always remember that the little x kind of goes with this, because eventually, foreshadowing, is that we're going to start talking about pairs of random variables, right? So for example, I might talk about the CDF of two random variables at once, like this, right? And then I'd have to figure out, okay, which one of these goes with which one of those. It would be like very confusing to keep track of which one is which, right? So it's a little confusing now, but I think it will save us confusion in the long run. And if I started doing it the other way, I think that you would be reviewing the book and be like, I don't understand what the difference is between this guy using X and this guy using Z or Y or something like that, right? What about X and X1? You could do it that way, right? So I'm not going to change. You can't change me. I'm sorry. But I understand the concern. And when it seems confusing, just ask me or I will clarify, right? I mean, I think that you're never really going to see, a different way of thinking about this is that you're never going to see the big X anywhere on the right-hand side, right? Everything on the right-hand side is always going to be the little x, right? The only time you see the big random variable is kind of in the subscript of the CDF, right? As a little reminder to say, okay, what random variable am I talking about, right? So hopefully that alleviates it somewhat because you're never going to have any big stuff on the right-hand side. Okay, that's a good rule of thumb. I saw a question over here. No? Another suggestion about how to improve my notation? Okay. All right, other comments or questions? So let's go back to the CDF with the uniform random variable, okay? So I had a picture. Let me go back to it. So for example, here, now I could write down this equation of the CDF, right? So in the example, we can write the CDF as an equation. And usually, the CDF is broken up into pieces, right? So in this case, I've got a piece that is 0 when I am less than 70, and I've got a piece that is 1 when I am greater than 90. And in the middle, what I have is this linear function. And I can see that this linear function is going to be given by x minus 70 over 90 minus 70. If you think about this, it's basically saying, you know, what percentage of the way am I to 90 starting at 70, right? And so then if I wanted to ask, okay, what's the probability that x is in the range 75 to 82, right? I could plug that in and say, okay, I just have to compute the CDF at 82 and the CDF at 75 and subtract those two things, right? So what is that? That's 85 minus 70 over 20 minus 75 minus 70 over 20. So it's 15 over 20 minus 5 over 20. Wait a second. That's not right. 82. 12 over 20 minus 5 over 20 gives me 7 over 20. Right? And that's really what the homework coming up is all about, is just basically evaluating CDF numbers. Should be an easy homework, actually. And this kind of makes sense. This is like saying, okay, well, I basically have a 7-unit wide interval. The whole interval is 20 units wide. And so since everything is uniform, the probability of getting that is 7 over 20. That kind of makes sense, right? And in general, I could think about a more general, what was it with me in general thing? So more generally, if I have a uniform distribution between A and B, two values, what would the CDF of that look like? Well, it's going to be 0 when I'm less than A, it's going to be 1 when I'm greater than B, and it's basically going to be, you know, how far along am I when I'm between A and B? And so the nice thing is that, you know, you should be able to convince yourself that for your typical continuous random variable, that these endpoints are always going to be consistent, right? And so you're going to notice in the homework that I defined for you a couple of CDFs that are kind of made up of different pieces, right? And so if you're not sure, you should always be able to convince yourself, okay, by plugging in, you know, for example here, by plugging in 70, right, for x, I can see that I get 70 minus 70 is 0. So I know that these two pieces line up. And 90 minus 70 over 90 minus 70 is 1, so these two pieces line up, right? So every CDF that you see or that you compute should basically hook up together at these, you know, joining points, okay? I mean, it is possible to design, and I do have one example in the homework, a really nice smooth CDF that doesn't have any if-then kind of statements, but for the most part, you always have this kind of part about, you know, what's happening before the action and what's happening after the action, okay? So what we're going to do, just as a preview coming up, is, you know, next time, now that I've defined this concept of a CDF, we're going to, number one, talk about this idea about what happens if I try to figure out what is the equivalent to the probability mass function when I've got a continuous random variable. And then I'll introduce for you a whole bunch of new named random variables, right? So just like we learned about a few named types like binomial, geometric, Poisson, that are your kind of typical possible discrete random variables, there are a whole bunch of typical continuous random variables that come up that you need to know about, and then we'll talk in some detail about each of those. So it's kind of like where we're going, okay? I guess one more thing that I'll say is that, you know, for those of you that are really, what's the word? You want to know everything, right? So it is possible, but just to head off any worries, but, you know, not likely in this class. This is just kind of like a little aside to kind of have a kind of a mixed, you know, kind of like a mixed discrete continuous random variable. Right? So, you know, for example, let's suppose that I'm waiting for my Uber, okay, or my Lyft. I think Lyft is more socially conscious. So let's suppose that I'm waiting for my car, okay? Now, maybe, you know, there's a probability that the car is already there waiting for me when I step out of my door, and that has probability P. And then the probability that the car is not there yet is 1 minus P, and so basically, if the car is there, I don't have to wait at all. If I have to wait, I could say, for example, that x is uniform on a distribution of 0 to 15 minutes. Right? So this is kind of a weird hybrid, right? Which is just for your reference, basically something like saying the CDF for this would look something like, you know, there is a non-zero probability that I don't have to wait at all, right? And that height is P. And then between 0 and 15 minutes, I kind of accrue the rest of my probability, right? And after 15 minutes, I'm sure I'm in the car, right? So this is kind of a weird hybrid of the stair-steppy world and the smooth function world, right? I don't want you to dwell too much on this because, you know, we're not going to talk about this going forward in general. This is kind of a corner case, but I think it's just worth talking about. You know, you could, in theory, mix up the discrete and continuous worlds to have some things that have really some probability of getting exactly that number, and then you have some parts that are more like continuous random variables, right? So don't worry about this too much, but I just wanted to say it for completeness, okay? And so just kind of saying, Oh, so first let me ask, any questions about this? Okay, so let's just say going forward, kind of what we have is, there's the discrete world and the continuous world. And we kind of first started talking about the, what am I trying to do here? So kind of in the discrete world, we kind of had this PMF, and we then just learned today about this CDF, right? And I also said, okay, well now we could kind of learn about a CDF in a continuous space, and next time we're going to kind of talk about what do we fill in the blank here, like what is the equivalent of the probability mass function when things are in the continuous world, right? And kind of the preview again is that since this is a integral and this is a derivative, that somehow what you expect to happen is that we're going to be differentiating the CDF, okay? And I think as I mentioned earlier, get ready for doing a bunch of integrals, right? That's kind of what's going to happen, not today, but next week is going to be time to do some integrals, right? Because we're going to mostly be talking about this new quantity, which is going to be called the PDF, the probability density function. And pretty much everything going forward we're going to talk about in terms of this PDF, okay? So that's going to be a key thing on Tuesday not to miss. So after you come back from your 3-day weekend, we're going to hit that one, okay? So any questions or comments?